Hello students, in the previous lecture I have discussed about the basic of a numerical weather prediction model and the fundamental seven equations. Out of 7 equations, 3 equations we have derived, which are the momentum equations along latitude direction, longitude direction and the vertical direction. Now today I will discuss about the derivation of continuity equation that is related to the conservation of mass. The mathematical relationship which expresses conservation of mass for a fluid is called continuity equations. Now, the Earth atmosphere is filled with fluid, that is air, water vapor. So, conservation of mass equation is important for analyzing those transportation of the air molecules. So, let us consider for dx, dy, dz is a volume element. For such a fixed control volume, the net rate of mass inflow through the sides must equal to the rate of accumulation of mass within the volume. This is the basic assumption. So the rate of inflow of mass to the left hand face per unit area, you just consider this volume element. How much mass is inserting? So from the left side, it is rho u minus del x of rho u del x by 2. So this is where rho is the density and u is the velocity component. So similarly, the outflow equals to rho u plus del x of rho u into del x by 2. For the x component of the velocity component, we have represented this. Now the net rate of flow through the area by this area covered by dx and dy, similarly this one and this one, we can write this one from this and this. So del y and del z will be multiplied. Now so how much is inserting? It is going this side. So these two side is opposite direction because we are considering inflow. That's why we are giving minus sign. Now similarly for the y and z direction, we can write same equation. Okay. Now, so combining these three, dx, dy and dz, we can write mass inflow per unit volume is minus grad of rho u. So from this equation, we are converting this one, gradient of rho u. The increase of mass per unit volume is rate of change of density is equals to minus grad of rho u. Okay, so if we sum it, we get this equation. So this is the equation of continuity. Now from this gradient of rho u, we can write this one, and if we put t dt, if we convert, then del t plus u dot del. Okay, so from here we can write 1 by rho del t plus gradient of u equals to 0 if we consider these two. So that was the continuity equation. As we have discussed, the final form is 1 by rho equals to del t plus gradient of u equals to 0. This is the equation of continuity. Hello students, in the previous lecture I have discussed about the basics of numerical weather prediction model and the fundamental 7 equations which are used in numerical weather prediction model I have described. Out of that 7 equations, 3 equations we have derived last day. Now today we have I'll show the derivation of one of the important thermodynamic energy equations, that is the conservation of energy. The first law of thermodynamics is usually derived by considering a system in thermodynamic equilibrium, that is a system which is initially at rest and after exchanging heat with its surrounding and doing work on the surroundings, it again at rest. For such a system, the first law states that the change in internal energy of the system is equal to the difference between the heat added to the system and the work done by the system. A Lagrangian control volume consisting of a specific mass of fluid may be regarded as a thermodynamic system. That's why in this derivation I'll use the Lagrangian formulation. So for that, let us consider a volume element or dx, dy and dz, similarly like the previous derivation. Here this plane is the y and z plane. Now we know that pressure is equals to the force per unit area. Therefore, the rate at which the surrounding fluid work on the volume element due to the pressure force on the two boundary surfaces in y and z plane is given by Pu surface A delta y delta z. It is the area will be delta y and delta z minus Pu delta y delta z. As we can see, two direction is opposite to each other, that's why the minus sign is coming. Now if you do the Taylor series expansion of the term Pub, we can write Pua plus del x of Pu x dx plus the higher terms. Neglecting the higher terms, what we can write Pub minus Pua dy dz delta y delta z equals to del s of Pu at surface A and delta V, the volume element delta V. Similarly, for the y and z components, what we can write minus del y Pu with the volume element multiplied by the volume element and minus del z Pu multiplied by the volume element. Okay. Therefore, the net rate of working by the pressure force is given by minus gradient of rho u delta V. This one. As already discussed, a Lagrangian control volume consisting of a specific mass of fluid may be regarded as a thermodynamic system. That's why we are using as a Lagrangian formulation here. So for that purpose, let us consider E is the internal energy per unit volume, unit mass. The total thermodynamic energy contained in a Lagrangian fluid element of a density rho and the volume delta V can be given by this one. You have to remember this for Lagrangian fluid. The total thermodynamic energy will be rho E plus half U square. That is the. Now, from the conservation of energy, this energy should be equal to the other energies on the system. So, there, the rate of change of this is equals to, this is that thermodynamic energy already we have derived. This part come from the body mass energy, means like the gravitational energy and the Coriolis force parameters. But as Coriolis force acting on a system is perpendicular to the velocity, that's why Coriolis parameter is not, it is not here. Only the force due to gravity is included, and the third one is due to the heating effect on a system. Okay, where Q dot is the heating rate per unit mass due to the radiation, conduction and latent heat release. Now from this equation, if you just make a simple derivative, left side will get this one, from this we are getting this one, and right side will be same. So just gradient we have converted. Now you can see G, this is vector, and here we have written rho GW delta V. GW means because G is given by G minus G K cap. The gravitation acts only in the vertical direction but downward direction, but K vector is in upward direction, that's why negative sign is coming. Okay, and the last term is same. Now simplifying this, okay, another thing is this part rho and delta V both are constant, that's why this part will be vanished. Now the left part will be this one, and again from the momentum equation we can write this one, rho ddt of half u dot u equals to minus u dot grad p minus rho GW. Okay, so if you write this in different way, we'll get rho dE dt equals to minus P grad U plus rho Q dot. Okay. Again, from geopotential equation, we know GW equals to Z dz dt. Okay. Vertical height, rate of change of vertical height is the vertical velocity. That's why it is called d phi dt multiplied by G. Now here, if we put this value, okay, then d dt will be coming out, and half U dot U plus phi equals to minus U dot grad P. Okay, from these two equations. Now these two equations are these two sum is the mechanical energy. Now from the continuity equation, what we know, 1 by rho del T plus grad of U equals to 0. Now we can write 1 by rho grad of U equals to minus 1 by rho square del T equals to, we are defining this as a d alpha dt. Okay, alpha is a specific volume. Now from the equation 1, rho del dE dt equals to minus P grad U plus rho Q dot. From this equation, we can write dE dt equals to minus d alpha dt plus rho Q dot, because the first term is equals to minus d alpha dt. Again, for any air, energy per unit volume is E equals to EVT. Okay, sorry, this is CV, that is specific heat at constant volume. Now if we make a derivative here, CV dt plus P d alpha dt is equals to Q dot. This is the usual form of the energy equation. Okay, you may have seen like this, CV dt plus P d alpha equals to dq. So Q dot or Q dot, small q dot we can write. Okay, so this is the form, the usual form of the energy equation.